have it.
And okay, okay. This is very basic content what I am going to tell you, but as it is a requirement in the sense the composite material also behave in the similar fashion. So you know that when you heat any object, okay, mostly metallic objects, okay, what is happening? Why it is going this way? Just wait. Yeah. When any object like mostly metallic object, when you take metallic object and heat it, okay, what you found that what you observe that if there was a initial, if it is an initial diameter, if it's a two-dimensional geometry or a three-dimensional geometry, in all the cases you will find that the material is expanding. This is, it happens due to the lattice vibration happens at the lattice point, okay, and that causes the elongation of the body, okay, something like that. And this feature is, it is one of the important feature that has to be addressed, because what happens in many engineering applications, like if you see here, okay, you know, this is the two sections of a bridge. This is the one section of bridge, and this is another section of bridge, okay. So you know, in the in between the bridges, these are called as some pi girder, some name they have given, okay. Just you assume that these are some connectors, okay, to connect these two bridges, okay. So you see here there are gaps are left in between these two, okay. So what happens during summer season, when the temperature is higher, then this entire structure will expand, okay, and this will cause, okay, in that case it will come it will expand and this gap will be filled. So in absence of such a gap, if they make the structure an integrated one, like this integrated one, there is no such arrangement is there, then what will happen, when their expansion is there during summer season, you will find local buckling in the structure, okay, because it will try to move like this, okay, and at the interface you will find some hill formation is there. To avoid such thing, some gap is left in between the two places. Actually here what is there, some gap is left, so that during the you know, when the temperature is high or expansion is there, then this gap itself is filled by the expansion, the extra expansion of this one. So this is one of the property of engineering materials, that when it is heated, it will change its dimension, okay. And to what is the measure for that one is the CTE, coefficient of thermal expansion, okay. What is this one, it is defined as the change in the linear dimension of a body per unit length, per unit change in temperature, means how the change is happening per unit as per the rate of change, means how the material is changing per unit time, means per unit length, like if the length was 1 mm, and there is a change in temperature by 1 degree centigrade, okay, then this 1 mm changes to how much. So that change we measure using the coefficient of thermal expansion, okay. So this is the observation which is formed for most of the engineering materials, okay. And so in the similar our composite materials also, they will behave like this only. What they will do, when it is heated, the composite materials are heated, it will expand. But you know, there is a difference here. This material I have shown you here is maybe steel, it is steel. So when it is steel, that means I can assume this is as isotropic. When it is isotropic, means coefficient of thermal expansion alpha will be same in all direction. That means if the material is like this, okay, and it is heated, then it is expanding. It is expanding, okay, it is expanding, okay, and uh, uh, or no, it is expanding in all the dimensions, in all the way it is expanding in the uh, maybe x and y. If I put like this, then it is expanding in the x direction as well, and expanding in the y direction as well. So this coefficient of thermal expansion in the x direction, if I put as alpha x, and coefficient of thermal expansion in the y direction as alpha y, if it is a two-dimensional geometry, then these two values will be always same, because this is an isotropic material. And what is isotropic material? That tells you that the material property or engineering constant of that material will be always constant in all the direction. Okay, like Young's modulus is there, Poisson's ratio is there. This we already have seen. See, in the similar fashion, coefficient of thermal expansion, conductivity, all the things are material property. So for isotropic material, this will be same in all the direction. However, composite materials are known for their anisotropic nature. Okay, anisotropic nature. Okay, so when anisotropic comes, that means it is going to dictate the thermal expansion as well, because we have seen in the composite material, if I have Young's modulus in one direction is E1 or Ex, then in the y direction I have Ey. Okay, and these two are not equal in composite material when it is a anisotropic material. In the similar fashion, the coefficient of thermal expansion in x direction, coefficient of thermal expansion in the y direction are not equal. Okay, because this is the inherent anisotropy is there. So so what happens in that case? See, already we know that we start with the Young's modulus and the volume fraction of fiber and matrix. These are the input parameters. This I should know. Okay. And if I know the coefficient of thermal expansion of fiber alone, coefficient of thermal expansion of matrix alone, then with this formula, I can get the value of coefficient of thermal expansion in the one direction like this one. So what does one direction means? One direction means when I am measuring the coefficient expansion along the fiber direction. Fiber direction is always called as one direction. This is also called as sometime in, if you read other literature, they will write as material direction. Okay, it is also written there. So this is the thing. So in this direction, coefficient of thermal expansion is called as alpha 1. So you see, these are the functions of your, what are the things you need to have the value of coefficient of thermal expansion of fiber, matrix, volume fraction of fiber, volume fraction of matrix, then your then your Young's modulus in of fiber alone, Young's modulus of matrix alone, then you have the Young's modulus of the composite material as a whole in one direction. Okay, okay, like this one. Okay, so this is about in the one direction. Okay, now when it comes into the second direction, okay, in the second direction, you have alpha 2, alpha 2. So you see alpha 2 has what are the things required here? I should have this one, coefficient of thermal expansion of fiber, matrix, volume fraction of fiber, matrix and fiber, and you have an additional terms are there, that is the volume itself, volume of the fiber. It is volume fraction, this is volume of the fiber, this is volume of the fiber, this is volume fraction of the fiber. And then you have this thing also, you see here there is a contribution of your thermal expansion. If you want to calculate the thermal expansion in two direction, you should have the value of thermal expansion in one direction. This is all long derivations are there in the books. Okay, I don't want to take you to that mode, okay, where you will see all the derivations, because anyway we are not going to ask the derivation in exams. Okay, long derivations are there, so just I am putting the working formula here. You see here, so in order to get the value of this, it all things are happening due to anisotropic behavior. When anisotropy comes, these all the material constants are sometime are interrelated with each other also. So that is the reason you see alpha 2, if you want to know, means the coefficient of thermal expansion in the two direction. Okay, in fact that two direction and three direction will be same here. So alpha 2 will be always equal to alpha 3. However, that will not be equal to alpha 1, because alpha 1 is in the fiber direction and these two are in the transverse direction. This is also transverse direction and this is also transverse direction. So these things are there. So you need to get the value of alpha 1 before, and this is the this is the Poisson's ratio in the 1 2 direction. In this plane 1 2 plane, you should get the value of Poisson's ratio. Then you can get the value of coefficient of thermal expansion. Now, just as an example here, if you see glass epoxy, glass epoxy is one of the common and highly adopted composite material due to its low price actually, because Kevlar epoxy and carbon epoxy, those are expensive one. So glass epoxy is easy to, not easy means it is less expensive in comparison to other composite material. So this is an example of a glass epoxy. And you see, as the volume fraction varies, volume fraction of fiber varies, what is the the different value of coefficient of thermal expansion. So you see here, coefficient of thermal expansion, okay, in the longitudinal direction, that means one direction. When the fibers are like this one, when the fibers are like this one, I am measuring, this is the one direction and this is the two direction. So coefficient of thermal expansion in one direction is always less as compared to the coefficient of thermal expansion in the two direction. What is happening actually here? Fiber fiber are very stable in nature. Okay, when the expansion is happening along the one direction, that means most of the contribution is taken by the fiber. Okay, and when it is expanding in the two direction, means matrix is actually expanding, matrix material is actually expanding when it is happening in the two direction. And matrix material are, it is a mostly plastic material. Okay, and when heat is applied to then it expands readily, it expands too much as compared to the fiber. So that is the reason you can see most of the for most of the values of your all, in fact I should say almost for all the values of for fiber volume fraction, the coefficient of thermal expansion in longitudinal direction is always less than your coefficient in the transverse direction, because here the transverse direction, it is mostly controlled by matrix expansion, and here it is controlled by fiber expansion, and fiber expansion is less, so the your coefficient is also less. Okay, so it is like this. And when we are talking when we're looking into the different types of fiber, we found that there are few fibers for which coefficient of thermal expansion is negative. I think if I recall, Kevlar was one of the fiber, which has got a very good thermal property. No, means strength and stiffness, corrosion property, lot of things. It has very good impact property, failure behavior, failure properties, crack initiation and propagation is very difficult in Kevlar. But one of the important drawback was there in the Kevlar, that it has negative coefficient of thermal expansion. That means if you heat Kevlar, then it will shrink. Okay, this you can observe also if you take a piece of polythene, what we use for carrying our stuff. Okay, maybe fruit or vegetable you bring from house for home. You take a piece of polythene, okay, and just you take a matchstick, okay, and just you put your matchstick near it. Okay, you will find that it is shrinking. It will shrink and it will become small. So what does it mean? Because it is telling you that on the application of heat, the molecules are coming close instead of moving further. They are coming close and contracting. That is shrinkage, and that happens reverse in case of metals, where the molecules move away from each other. Okay, so such things are happening in the Kevlar material. So negative values are also it's a true it is a truth that negative value of coefficient of thermal expansion has been observed in many fibers. So you see, on the one hand, you have positive value of CTE. CTE is positive, and you have negative. So that means if you work out and if you try to find out some of the this one composite material which will have zero CTE, there are chances that if, because fibers, if some fiber has positive CTE and some has negative CTE, then definitely there will be some fibers which will have zero CTE. And this is one of the property of composite material, which has made few, not all composite materials, few composite materials, which has made them a very good candidate materials for making antenna, doors of your aircraft. Okay, aircraft or space shuttles, spaceships. Okay, where there is a temperature difference, but what will happen, though there is a temperature rise or there is a temperature fall, like you see the cryogenic application, cryogenic application. Cryogenic means when the temperature is very low, very low. Cryogenic engines have been developed and our India along with Russia, they have developed this cryogenic engines which operate at very low temperature. Cryogenic engine. So in such applications, if the composite materials are used which has got zero coefficient of thermal expansion, that means nothing is going to happen to the structure. The structure will be always stable and it will always retain its shape, though there is any fall in the temperature or rise in the temperature. So this property is actually one of the property of not all but few composite materials which shows a coefficient of thermal expansion zero. So this I wanted to share with you that this is one of the thing that composite material has gained much popularity in space application. Now coming to coefficient of moisture expansion. Okay, what happens? I think if you have seen in your home that if it happens if you see your wood material or a door which is placed at the front of your house or the backyard of your house, where you are continuously it is getting rainwater or rainwater like that, then what will happen? Your wood will become like this. Are you able to see? Just confirmation from your end. Hello, is it
Sir,
audible?
yes, sir,
Yes,
audible.
yes.
Very
Okay,
little part of that figure is visible.
figure is little.
That, yeah, that hole is visible.
Whole is not coming. Okay, at least you are able to see some part.
We are able to see the hole, but yeah, the figure is not very clear.
Okay, but here it is showing full screen. I don't know what is happening. So what is happening here? So you see that wood, it will become like this. It will absorb moisture, okay, and it will start deteriorating. Okay, the strength wise it is deteriorates very badly like this one. But such thing what I have told you, here also you can see the moisture what it observes, that is deteriorating mostly along the transverse direction. You will not find the along the fiber direction or along this direction there is much distortion. You see here, it is piling up. The piles which are the different layers are there, they are actually separating out. So this means that along the transverse direction, not along the fiber direction, that the fibers are breaking or anything is happening. No, but fibers are remaining same. You see here, fibers are same like this one. But you see, in interlaminar failure means inside the fiber, between the two layers of the fiber matrix material or fiber, there is a failure is happening. So such thing is observed in composite material. This is wood. Wood is also a natural composite material. However, if you see that this one, the artificial composite material, you see matrix is there, this is matrix is there, this is fiber is there, and the moment some amount of moisture comes, okay, starts going inside one moisture. This matrix material absorbs moisture, and when moisture are there, yeah, it will actually start expanding. And when it expansion happens, there is always in a bond between the fiber and matrix, okay, and this bond actually starts breaking, okay, and you get that the strength of your composite material as a whole has reduced a lot, because lot of the at interface, this is called at the interface, fiber matrix interface, at lot of the position, you find that the interface has broken, or the matrix has lost its connect with your fiber, so the strength as a whole of the composite material will come down. Okay, so this is the addition thing that what happens when in composite material absorbs moisture. Okay, so similar to the coefficient of thermal expansion, okay, it is this moisture, the coefficient of thermal expansion, the coefficient of moisture expansion, okay, as it is an anisotropic material. Okay, so you will have two coefficients, I think beta, they are writing beta 1 beta 2, coefficient of moisture expansion in one direction, coefficient of moisture direction in two direction, like this one, and beta 2 will be equal to beta 3. Okay, because transfer direction is same always. So these are the expression for the coefficient of moisture expansion in one and two direction. Okay, you see here very very long expressions are there, and in fact in this expression you see that there is apart from volume fraction and like volume fraction of fiber, volume fraction of matrix, and the Young's modulus of fiber, Young's modulus matrix. Apart from them, you have some contribution of these terms also. Contribution from these terms. What are these terms? These are the moisture concentration in the fiber, kg by kg. How much kg of moisture is there in per kg of fiber? It is a ratio like this one. So you see here, those things are also playing a role here. You see here. Now, question is that why it is coming like this one? Okay, because I don't see any concentration of any such thing in case of thermal expansion. Okay, why this is happening here? The formulation has been developed in such a way because you know fiber and matrix both are different entities. Okay, and even after mixing as a composite material, they are still different, though they are going to give you a third material which has got a which inherits its property from both fiber and matrix, but still you can find that there are two distinct materials mixed together and which is forming the composite material. And the absorption capacity of moisture for fiber and matrix are different. It is not that they are both of them will be absorbing the same amount of fiber, same amount of moisture. That is the reason when the formulation was developed to find the coefficient of thermal moisture expansion for composite material in one direction and two direction, the concentration terms were also introduced here. You see here. You see here density is also there. Density is also there. Okay, and this is for the one direction, and when it comes to the two direction you find that additional some terms are coming. What are the additional terms are there? Volume of the fiber, this is volume fraction. Vf is the volume fraction, this is volume of the fiber. So lot of if you book which I am referring is uh, uh, a cow. This is the book which I am referring. Okay, you can refer other books also, and what the textbook is prescribed to you. But in all the books if you find that when they start the derivation part, they're very very lengthy process. Okay, derivations are very very lengthy. So I'm just putting you the working formulas here. So let's see what are the different quantities here. Delta Cf, moisture concentration in the fiber, kg by kg. Okay, delta Cm, moisture concentration in the matrix. Okay, what is Bf? Coefficient of moisture expansion of fiber, my expansion of matrix, and B1, beta 1, beta 2 is the linear coefficient of moisture expansion in direction 1 and direction 2. So this is the way the thing has been developed. So other things are also there. Now you see here. Uh, this is what I wanted to tell you, that it didn't happen in the case of thermal expansion, that where you are getting the effect of concentration of moisture in the concentration in the formula. Like I didn't have any concentration for temperature, something like that, but here I are finding that the concentration of moisture in the fiber and the matrix, that is also playing a role in determining the coefficient of moisture expansion for the composite material. This I have told you. But what happens? Actually, I told you that matrix, actually, when composite, I tell composite material, that means it has fiber, it has matrix. So, and these fibers are mostly inside the composite material. Okay, and they absorb very minimal amount of moisture. Most of the moisture is absorbed by my matrix material. Fibers means very very minimum. So what happens in that case, for mostly polymeric composite material, where matrix is polymer, okay, which is absorbing most of the moisture. Okay, fiber don't absorb moisture. So that in the expression for coefficient of moisture expansion, we can put easily that there is no moisture present in the fiber. You see here this formula. Here I can put this term 0, this term 0. Here also I can put this term 0 and this term 0. So what will happen? So this expression, long expression, simplifies very well like this one in this formula. It becomes independent of moisture content. That means, but you have to assume, you have to see that I have written in most of the polymeric composite material, not all composite material. So in the polymeric composite material, easily you can make this assumption that this is a polymeric composite material, and here I can assume that the moisture which absorbed by the fiber is very minimal. Okay, in that case my my formula for the coefficient of moisture expansion beta 1 becomes like this one, independent of, the moment I put Cf is equal to 0, then this expression become independent of both Cf and Cm, independent of both the things. It becomes, this is a very beautiful expression. I should say that if one is assuming 0, you are assuming 1 is 0, then it becomes independent, because here you are putting this 0, this 0. However, these things are there, so it cancel out. Here it gets cancelled out, these two things, and become independent. So in the case of polymeric composite material, directly we can write the coefficient of moisture expansion like this one. Okay, here also this is for the one direction. For the two direction, the similar operation you can do, and you get an expression like this one, independent of both delta Cf and delta Cm. It becomes independent of both the things. So till now in the micromechanics part, when we looked into the micromechanics part, what we have seen, we observed that here I will make a difference between micromechanics and micromechanics. Here what we have seen, that okay, there was fibers were there in the composite material, fibers were there arranged in some fashion, and matrix was there. This is the matrix material and this is the fiber material. Okay, it has got some Young's modulus ef, it has got some Young's modulus em. Then we are going to find the Young's modulus in one direction, Young's modulus in two direction, which is a function of which is actually a function of fiber volume fraction, matrix volume fraction, then ef and em, and somehow we are going to get this one E1 and E2 value. So this we are looking into very in a detailed fashion. Okay, but this is the approach in the macro mechanics. This is the approach in the micro mechanics. In macro mechanics we are doing like this one. However, in the macro mechanics, when it comes to the macro mechanics, we don't look into em, volume fraction and this thing. We directly take the composite material for our analysis. Okay, and I just assign what is E1, what is E2, like this one, what is new 1 2, new 2 1, what is G1 2, what. This means actually the precursor for the analysis of macromechanics. Okay, macromechanics means I am taking the composite material as a plate or slab or a block like this one. Okay, not like this one, that I am seeing the fiber also and matrix also, and I'm just doing analysis with a small pieces like this one. No, I'll assume that composite material is like this one. Okay, big layers of fiber and matrix are there. Okay, but I'm not concerned that how the distribution is there and how the alignment is there. I'm not concerned. I'm taking as composite material as a bulk material now, as a bulk material directly, which I can use directly into my structure. Okay, and like if I want to make a uh, turbine blade, or maybe a wind turbine blade. Okay, okay, like this one, which is going to do power generation for you. Okay, and I want to analyze that what is the forces getting applied when the turbine getting blade is getting will fail, and when it will bend, or when it will distort. If I want to do the such analysis, I will go to the micromechanics mode, where I will ask that give me these values for the composite material. Okay, and I'll do the analysis. I will not bother about this one, that what is fiber volume fraction, what is this one, this thing, these things. These are the things which are actually required to find these things. Okay, all the things are required to find this thing, but I am but on the larger picture, I just need these values. Okay, I'm not going to calculate, I'm not going to do the derivation or anything. This is called the micromechanics. That was the micromechanics approach, but in the micromechanics I am taking composite material as a bulk material, a larger picture of the composite material, and here I am going to do the analysis. So this is the part we will start tomorrow onward. So what till now, what we have discussed, we looked into what is fiber volume fraction, weight fraction, and then we looked into the elastic modulus of unidirectional lamina. Okay, now this thing what I am telling you is lamina. We are doing it for lamina, means single layer. Okay, there is one layer, a lot of fibers are there, and matrix is there. Single layer, for single layer lamina, these things are there. Okay, we find all the things, but now we will have laminate. This is, here it is called as lamina in micromechanics, lamina, and here it is called as laminate. Combination of lamina, lot of stacking of laminas are there to make laminate, and we do the actual analysis. We do the actual analysis on laminate. Okay, no one is going to lamina alone, one layer of fiber and one layer of what is called as matrix material and making a structure. No one is going to do like that one. Everyone will use different stacks of the fiber, different collection of the fiber lamina together, put together, and making laminate and doing the analysis like this one. So these things we already have seen. This was the part which I wanted to discuss with you in the macromechanics part. So this already we have seen that based on your fiber volume fraction, and if you know the individual Young's modulus or other mechanical properties also like GF, GM, then you can find the value of E1 and E2 like this one. And once this you get the this give the E1 and E2, this becomes a precursor or input for doing the analysis in micromechanics mode, where the material will be used as a structural application, directly as a structural application. So this was the summary. Whatever the things we have done till now, we looked into the thermal expansion, moisture expansion, then elastic modulus, and the different approaches to find the elastic modulus, like strength of material approach, that is called as mechanics of material approach also. Then help and psi assumption, which is semi empirical in nature. Then we looked into the approach from elasticity, and we found that the elasticity approach is one of the best approach to find the elastic modulus for a unidirectional lamina. However, it is a very means the derivation part, it requires lot of working there to understand the thing and get it done. Okay, but this what is the results are very good as when we compare with the experimental data. So up to this, let's close this one. That macro mechanics we are done with the macro mechanics part, and tomorrow onwards we will start with the real part of the composite material, when we are taking the composite material as a whole. Okay, whether we can assume that composite material is isotropic or not, what is transversely isotropic, what is orthotropic. These are going to be very important. If you tell someone that I have done a composite material course and I know composite, they will ask you that what do you mean by orthotropic material, what do you mean by transversely isotropic material. These are the things which immediately people will ask you, and they expect you to know these things very well. Needless to say, these things will be very easy for you. Tomorrow onwards we'll be looking at all the things, and then we will look into the failure of lamina, then your failure of these things, failure of laminate as a whole. Okay, then we will go into the some of the design part of this one, that how you, based on some design criterias, how you will design a composite material for a particular application. Okay, so this is all from my side. I'll just immediately share the slides with you so that you can have with you. So we will meet tomorrow again, okay, around after this one, and we will do the thing as and when it is required. We will not wait further. Anything else from your end? I'm stopping the recording now.